87% of AI companies are burning cash on the wrong cloud infrastructure, and they have no idea.
Wrong infrastructure? What are they missing? So we're breaking down these 6 categories, who fits where, and how to pick the right one?
By minute 7, you'll know exactly which provider type matches your workload. Let's get into it.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're diving into a practical guide to the 6 categories of AI cloud infrastructure in 2026.
Stick around to the end for today's headlines. Let's dive right in.
So let's talk about the fundamental shift happening in AI cloud infrastructure. Platform teams are drowning in choices right now. It used to be AWS, Azure, or Google Cloud. Pick one and move on. But in 2026, we're looking at 6 distinct categories of AI cloud providers, each optimized for completely different workloads and team profiles.
6 categories? That seems like a lot of fragmentation. What's driving all this specialization?
The biggest driver is the split between training and inference workloads. Deloitte's 2026 predictions show that inference now accounts for roughly 2/3 of all AI compute. That's a massive shift from just 2 years ago when training dominated the conversation. But here's the thing. Training a foundation model requires completely different infrastructure than serving millions of inference requests.
Right, and I imagine the economics are totally different too. Training is about raw compute power, but inference is about efficiency at scale.
Exactly. And that's created this whole new market dynamic. Take OpenAI as an example. They've got major compute partnerships across AWS, Oracle, and CoreWeave, while Azure remains central to their production stack. They're not just multi-cloud, they're multi-category. They use traditional hyperscalers for some workloads, neoclouds for others, and even specialized inference providers for certain use cases.
But doesn't that create operational complexity? Managing relationships and workloads across multiple providers sounds like a nightmare.
It absolutely does, which is why having a clear taxonomy matters. Without understanding what each category optimizes for, teams end up defaulting to whatever provider they already know. And that often means overpaying by 40 to 60% or dealing with constant availability issues. I've seen teams burning through their entire quarterly budget in 2 weeks because they picked the wrong provider for a training job.
Ouch. So walk me through these 6 categories. What are we looking at?
First, you've got your traditional hyperscalers, AWS, Azure, Google Cloud, Oracle. These are the full-stack clouds with GPU instances alongside their broader enterprise services. They excel at ecosystem integration and compliance, but they're typically the most expensive option and have the worst GPU availability.
And the neoclouds are the opposite.
Neoclouds like CoreWeave and Lambda Labs are GPU native from the ground up. They were built specifically for AI workloads, so they can offer better pricing and availability. CoreWeave, for instance, typically runs 30 to 50% cheaper than AWS for equivalent GPU time. But you lose that ecosystem integration. No native databases, no managed Kubernetes, none of the enterprise bells and whistles.
So it's a trade-off between cost efficiency and operational overhead.
Precisely. And that's just the first 2 categories. Coming up, we'll dig into exactly how specialized inference providers, developer platforms, edge providers, and sovereign clouds each fit into this ecosystem. Plus, I'll share a decision framework that's helped dozens of teams pick the right provider for their specific workloads. Let's dive deeper into these categories because the differences are pretty stark. After the traditional hyperscalers and neoclouds, the third category is specialized inference providers. These are companies like Together AI, Replicate, and Modal that focus exclusively on serving models, not training them.
How different is their infrastructure from, say, a neocloud?
It's fundamentally different architecture. Inference providers optimize for request latency and throughput rather than sustained compute. They use techniques like dynamic batching, model quantization, and specialized serving frameworks. Together, AI can serve Llama models at 10x lower cost than running the same model on raw GPU instances because they're pooling requests across customers and maximizing GPU utilization.
That's clever. So they're essentially turning inference into a multi-tenant service rather than dedicated compute.
Exactly. And the numbers back this up. Running a Llama 70B model on AWS might cost you $3 to $4 per million tokens. On a specialized inference provider, you're looking at 30 cents to 50 cents per million tokens. That's an order of magnitude difference. But there are trade-offs. You get less control over the serving infrastructure, potential cold start issues, and you're limited to their supported model architectures.
What about data privacy if they're pooling requests?
Great question. Most providers offer isolated inference options for sensitive workloads, but it typically costs 2 to 3x more. It's still cheaper than DIY on hyperscalers, but the gap narrows considerably. The fourth category is developer platforms. Think Hugging Face, Weights and Biases, and increasingly, GitHub with their AI features. These aren't just about compute, they're about the entire developer experience around AI.
How does Hugging Face compete with raw infrastructure providers?
They're not really competing, they're abstracting away the infrastructure complexity. Hugging Face inference endpoints, for instance, let you deploy a model in literally 3 clicks. Behind the scenes, they're managing the infrastructure across multiple providers, handling scaling and optimizing performance. You pay a premium, maybe 20 to 30% more than going direct to infrastructure, but for many teams, that's worth it for the developer velocity.
Especially for teams that aren't deep in ML ops.
Exactly. And here's where it gets interesting. These platforms are becoming kingmakers in the infrastructure space. Hugging Face recently announced they're routing workloads across AWS, Google Cloud, and several neoclouds based on availability and pricing. They're essentially becoming a meta cloud for AI workloads. The fifth category is edge AI providers, companies like Fastly, Cloudflare, and Fly.io that are pushing inference to the network edge. This is crucial for applications that need sub-100 millisecond latency globally.
But edge compute is typically CPU-based. How are they handling AI workloads?
They're taking 2 approaches. Some are deploying specialized AI accelerators at edge locations, not full GPUs, but chips optimized for inference. Others are betting on highly optimized CPU inference. Cloudflare's Workers AI, for example, uses aggressive quantization and custom kernels to run smaller models on their edge network. You're not running GPT-4 on the edge, but for models under 10B parameters, it's increasingly viable.
That opens up interesting architectural patterns. Maybe you run a small model at the edge for immediate responses, then cascade to a larger model in a central location for complex queries.
Now you're thinking like a platform engineer. That cascade pattern is exactly what we're seeing in production. The latency benefits are huge. We're talking 10 to 50 millisecond response times for initial inference versus 200 to 500 milliseconds going to a centralized provider. The last category is sovereign clouds. Providers like OVH Cloud in Europe, Alibaba Cloud in China, and emerging national cloud initiatives. These matter because of data residency requirements and geopolitical considerations.
But don't they lag behind in GPU availability?
They used to, but that's changing fast. The EU's digital sovereignty push has driven massive investment. OVH Cloud now offers H100 clusters that rival what you'd get from hyperscalers, and they're often more available because they're not competing with the global market. The trade-off is ecosystem maturity. Their AI tooling typically lags 6 to 12 months behind the leading providers.
So how do you even begin to choose between all these options?
That's where a proper evaluation framework becomes critical. Stick around. We'll walk through the exact decision tree that helps you match workloads to the right infrastructure category. Plus, what changes are coming in 2027 that might flip these dynamics entirely. All right, let's get practical. Here's the evaluation framework we've developed after working with dozens of platform teams. It starts with 3 fundamental questions that immediately narrow down your options.
What's question number 1?
First question, is this a training or inference workload? If it's training, you're immediately down to hyperscalers, neoclouds, or specialized training platforms. The inference-only providers are off the table. For training, the next question is budget versus time. If you need GPUs tomorrow and cost a secondary, hyperscalers might be your only option, despite the premium. If you can wait a week or two, neoclouds offer 30 to 50% savings.
But what if I need both training and inference?
That's where it gets interesting. Most teams are finding that using different providers for different stages of the pipeline actually saves money and improves performance. Train on a neocloud where you get better GPU pricing, then deploy to a specialized inference provider or edge network. The data transfer costs are usually negligible compared to the compute savings. Second question, what's your latency requirement? If you need sub-100 millisecond inference globally, you're looking at edge providers or hyperscalers with global presence. If 200 to 500 milliseconds is acceptable, your options open up dramatically.
And the third question?
Compliance and data residency. This immediately tells you whether sovereign clouds are mandatory or if you can use global providers. But here's the nuance. Even if you don't have strict residency requirements, sovereign clouds can offer better availability and pricing for certain regions. We've seen European teams get 40% better pricing on OVH Cloud compared to AWS Frankfurt.
So once you've answered these questions, how do you make the final decision?
You build a simple scoring matrix. Rate each provider category on 5 dimensions: cost, availability, ecosystem integration, operational overhead, and performance. Weight these based on your priorities. For startup doing rapid experimentation, maybe it's 40% cost, 30% availability, 30% performance. For an enterprise, it might be 40% ecosystem integration, 30% operational overhead, 30% compliance. Here's a real example. A fintech startup needed to fine-tune Llama 3 and serve it to 100,000 users. Their scoring led them to train on Lambda Labs, saving $200,000 versus AWS, then deploy inference on Together AI with Cloudflare Workers AI for edge caching. Total monthly cost, $15,000. The same setup entirely on AWS would have been $45,000.
That's a massive difference. But what about the operational complexity?
It's real, but manageable with the right abstractions. Tools like Kubernetes Federation, Terraform multi-provider configs, and emerging AI workload orchestrators like Anyscale or Flight help manage this complexity. The key is starting simple, maybe just training versus inference split, then gradually adding providers as you understand the operational patterns.
What should teams watch out for in 2027?
3 big shifts are coming. First, we're going to see consolidation in the neocloud space. Not all these providers will survive, so avoid deep lock-in. Second, the hyperscalers are fighting back with dedicated AI regions that might close the pricing gap. AWS's Project Rainier is rumored to offer 50% lower GPU pricing in exchange for flexibility on availability zones. Third, on-device inference is about to explode. Apple's M4 chips and Qualcomm's latest NPUs can run 7B parameter models locally. That changes the entire edge computing equation.
So the landscape will keep fragmenting before it consolidates.
In the short term, yes. But here's my prediction. By 2028, we'll see AI workload brokers that automatically route your jobs to the optimal provider based on real-time pricing and availability. Think of it like a CDN for AI compute. Platform teams should build with this future in mind, stay cloud agnostic where possible, use standard frameworks, and avoid proprietary APIs. The teams winning in this environment aren't trying to pick one perfect provider. They're building flexible architectures that can leverage the strengths of each category. Start with your highest cost workload, apply this framework, and run a proof of concept with 2 to 3 providers. The savings usually pay for the migration effort within the first month.
This completely changes how I think about AI infrastructure planning.
That's the opportunity here. While everyone else is paralyzed by choice, platform teams that understand this landscape can deliver massive competitive advantages. The difference between picking the right versus wrong infrastructure isn't 10% anymore. It's 5 to 10x on cost and performance. In the AI era, infrastructure strategy is business strategy. Before we wrap up, let's catch up on this week's infrastructure news. There's a major security situation unfolding with AWS's new Managed OpenClaw service on light sale. InfoQ reports that while AWS just launched this AI agent deployment platform, it's shipping with critical vulnerabilities, including a one-click remote code execution bug.
Wait, they're launching with known vulnerabilities? That CVE 2026-25253 affects over 17,500 instances?
Exactly. It's a tough spot for platform teams. You get managed AI agent deployment, but with significant security risks baked in. AWS hasn't provided a timeline for patches yet.
That's going to make adoption conversations really difficult. Speaking of AI infrastructure, Sebastian Rashka just dropped something interesting, an LLM architecture gallery.
This is actually brilliant for platform engineers. It consolidates architecture diagrams and fact sheets for recent open-weight LLMs all in one place. No more hunting through papers and documentation.
So it's like a visual encyclopedia for LLM architectures? That could really speed up evaluation cycles when teams are choosing models.
Exactly. And speaking of making AI more production-ready, the new stack has details on the Model Context Protocol's 2026 roadmap. They're tackling MCP's biggest production pain points.
Finally, what are the priority areas?
4 key focuses: scalability, agent communication, and 2 others that directly address why teams struggle to move MCP from proof of concept to production. This could be huge for standardizing how AI agents interact with external systems.
Shifting gears completely, Linux kernel developers just landed something Windows has had for years. Cache-aware scheduling is finally here.
The Iowa Park leader coverage explains this minimizes cache misses and destructive migrations. Basically, the scheduler now understands CPU cache topology and keeps processes on cores where their data is already cached.
That's a significant performance win for platform teams running Linux workloads. Better cache utilization means lower latency and higher throughput without any application changes.
Exactly. It's kernel-level optimization that benefits everyone. That wraps up today's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
And check out platformengineeringplaybook.com for more resources and guides. Until next time.